I'm Joshua White, and this is my project on deep reinforcement learning and Atari Breakout. The purpose of this project is to learn how to apply deep reinforcement learning to develop a model that thrives or scores highly in a complex game environment using TensorFlow and Keras in Python. The game environment I selected to work with is the Atari game Breakout. If you don't know what Breakout is, it's the game visualized here, where the player controls a paddle at the bottom of the screen and attempts to bounce the moving ball against the colored bricks at the top. Doing so destroys the brick it's bounced against and provides points to the player. If the player misses the ball and it goes off the bottom of the screen, the player loses a life. The game ends either when all of the bricks are cleared or the player runs out of lives. I accomplished this task in large part due to these libraries managed by the Farama Foundation. Gymnasium is a fork of OpenAI's Gym library that allows me to easily train and connect my model to the arcade learning environment, which is how I emulate the game itself. So onto my methodology. I use an epsilon greedy Q-learning model to accomplish this task. Just as a refresher, Q-learning is a reinforcement learning algorithm that trains an agent to assign values to its possible actions based on its current state, without requiring a model of the environment. The epsilon greedy side of that signifies that a random action may be selected instead of a chance of epsilon. A random action may be selected with a chance of epsilon instead of the action with the highest Q value to encourage the model to explore and not get stuck in some local minima. As for how I evaluate Q value, I use a deep Q network, or DQN, that takes the state features as inputs, convolutes them, then outputs the Q values for each possible action. Let's take a look at how I actually implement this. Here, you can see the main flow of how I train the network. Let's follow along here. Firstly, an action is selected. Early on, this action is completely random. Then, the environment, in this case being the game breakout, responds in some way to the action, such as moving the paddle and bouncing the ball. Some reward may or may not be given for this action. In either case, the resulting state, reward, and everything is then stored in the replay buffer, which acts sort of as the long-term memory of the last, let's say 100,000, as an example, states and rewards that the model can train with. A small mini batch is sampled from this buffer for use in any given training loop and fed into two identical yet separate models. The main model is the active policy model, being trained to evaluate Q values of each action given a state. The target model is identical to the policy model, except its weights are only updated to match the main model every 1,000 loops, or however many you choose. This target model also evaluates Q values that serve sort of as the true values that we use to evaluate the loss in the main policy model. In this way, we have a sort of floating target that improves alongside the main policy model, yet keeps it grounded, keeps training consistent, and discourages divergence. From there, an action is once again selected according to epsilon greedy policy, and the Q value is evaluated from the main model, and the process repeats. And I can actually go through this flow in my code. Here's my main training loop. Here we can see that an action is selected via epsilon greedy policy. The environments are stepped. We'll go over this portion a little later. But anyways, everything is stored in the replay buffer and updated. And then the main training and updating to the networks is actually here, where I normalize the pixel inputs, calculate Q, select the action with my main policy network, and evaluate with the target network, and then update the weights, where we once again loop back around to pick the next action. So here's the model I used itself. While not specified here, the inputs are four stacked frames of 84 by 84 pixel images of the breakout game being played, and the outputs are the Q values calculated for each available action. I have also listed all available actions the agent can take at any given time, which is simply do nothing, fire, which only comes into effect for serving the ball when a game is started or after the player loses a life, and then moving the paddle right or left. As for the convolutional layers, I kept it pretty simple due to the extensive training required for this task. My main goal with this architecture was simply to capture as many different patterns, both high and low level, and as few layers as possible. I also wanted to include in my presentation a bit of a hurdle I had to overcome. This was that portion of the while loop I skipped before. Initially, as I was trying to train my model, it just wouldn't even use the fire action to actually launch the ball and start the game unless the action was randomly selected with the epsilon policy. That's because rewards are so sparse in this environment, meaning there are so many frames between the ball being launched, reflected by the paddle, and eventually destroying a block, that the delayed reward for this wouldn't even register, despite the extremely high gamma I used of 0.99, which means that the model did, in fact, value delayed rewards quite highly. To adjust for this, I manually edited the reward structure to provide some reward when the ball was served to encourage the model to actually play the game. Anyway, here are my final results from training over almost 136,000 episodes and 50 million frames. I actually had to vectorize my environments to train 64 games simultaneously, to run 64 games simultaneously, and be able to train my model in any reasonable amount of time. From the learning curve graph on the right, you can see that towards the end of training, the AI was able to earn an average of about 50 points for each game it played. At the bottom, I pictured one of the games my model played to give you a good idea of what that amount of points looks like, that game state. Looking back at the breakout learning curve, though, you can also notice the extremely gradual and steady upward trend. This exact shape is largely due to the fact that I linearly decreased epsilon from beginning of training to the end, but this continual upward trend in general implies that this model could continue to improve and score higher given even more training time. I actually want to visualize the improvement that this model made. At the start of training, you can see in the first 100 episodes or so, it would get an average reward of 1 point, meaning that most games were getting either one brick destroyed or zero, and the model was just moving the paddle around left and right randomly and accomplishing basically nothing. And I would like you to then compare that to the final version of my model, where you can see it won't play perfectly, it'll still lose lives, but it certainly has a much better idea and plays much more advanced uh, and is able to score quite highly. We don't have to watch this entire game play out. I just wanted to give you a general idea of the vast, vast improvement that my model made from accomplishing basically nothing to accomplishing this. So finally, I want to go over some pros and cons of my final implementation. For pros, I believe I accomplished answering my problem statement and developing a model that can improve and score quite highly in Atari Breakout. Another positive of my project is that I run 64 games simultaneously, which dramatically reduced the time required for training. Lastly, the separation of two networks for policy and target resulted in quite steady and accurate training overall. As for the cons, despite running 64 games at once, this model required a minimum of 12 hours to train and would likely benefit from even more training time. Also, the size of the replay buffer in my implementation is quite limited by the RAM I had available to me. Even a memory of just 100,000 frames, compared to the 50 million that I trained on, took roughly 6 gigabytes of my RAM. Finally, of course, my model doesn't actually beat the game by eliminating all blocks. I'll admit that training this model was much more resource and time intensive than I originally thought it would be, and I had hoped to push it to even higher scores. Overall, though, I believe this model accomplished what I set out to do with my problem statement and absolutely learned how to survive and thrive in Atari Breakout. Thank you.